So I have some series, right? Uh, right? The sum of a sub n, yes? And what I can do is I can look at consecutive terms, right? I want to look at the ratio of consecutive terms and look at that limit. So the limit in absolute value of a sub n plus 1 over a sub n could have several instances come out. If I get a limit that's less than 1, okay, and obviously it won't be negative here because of my absolute value. If I get a limit that's less than 1, this series will be convergent. In fact, even better than convergent, absolute convergence. So if I get a limit that's less than 1, then the series of a sub n is convergent. Now think about that. Absolute convergence means even if I have some negative and positive terms, if I cancel all the negatives, it will still add up. That's right. So think about this. What is going on? And by the way, this test is good, like Paul's note says, when you have x to n to a power or factorials. Okay? So you're kind of looking for that when you have it. So if I have like polynomials, if I have factorials, anything like that, this is a good test to try. It says if this limit is less than 1, then I'm going to get a sum. Think about that. Why? What is your thinking about if I get some limit out of this and it's less than 1? And remember, what I'm doing is I'm looking at ratio of terms, ratio of the terms coming to the term before it, right? What am I saying about what's happening to the terms here? Getting smaller. So certainly if they're getting bigger, there's no way I'm getting it right. I'm getting it to converge. If I have the limit greater than 1, it's going to diverge. Should be obvious, right? The limit of a sub n plus 1 over a sub n is greater than 1, then the series is divergent. And that should be obvious, right? Because it's saying, well, I'm going to keep adding bigger and bigger terms. If I keep adding bigger and bigger terms, there's no way I'm getting a sum out of it. And I think the last one is pretty interesting, is if I get a limit of 1, the ratio test is inconclusive. The limit of a sub n plus 1 over a sub n equals 1, you cannot conclude. Why? What do you think? I think the middle one is obvious, right? If I keep adding bigger and bigger things, there's no way I'm going to converge. The first one seems like, right, could still be trouble, right? But we're going to put that on hold for a second. But this one, I think we should be able to come up with it. Why do you think this does not give me? Say again. Okay, so but it says it can't conclude. It doesn't. It doesn't mean it necessarily. Right. Sometimes it could. If I have one like this, it could converge. Sometimes it could diverge. Right. But what's kind of special about what you're seeing? If I have a ratio of 1, what are you kind of thinking? Numerator and denominator. Okay, I like that thought. And then where are we going when we get an infinity over infinity? L'Hopital's. L'Hopital's rule sometimes will give me, right, or 0 over 0, but sometimes it will give me a limit of 0, or sometimes it will give me no limit, right? So when I'm in that situation, I can't really tell what's going on because L'Hopital's rule isn't always going to give me a limit, right? It could go to infinity, right? So, but we're going to start looking at power series, and we're going to use this ratio test to look for convergence. So, for example, and again, I'm saying, right, I'm saying, so let's take one we know converges and look at the ratio test for it. So let's take a sub n equals 1 over n squared, right? We know this one converges already by the integral test, correct? So let's see if we get the same result out of it from the ratio test, right? So we want to try the ratio test here. So I'm looking at the limit as n goes to infinity of 1 over n plus 1 quantity squared over 1 over n. Oh, sorry, n squared, right? So I'm putting in the next term, right? So I'm changing the n to n plus 1 for the next term. On this particular one, I don't even need the absolute value, correct? So a lot of times you'll decide if you need the absolute value or not and then rip it off if you don't need it. But what happens here? We're going to do a little algebra, a little arithmetic, right? Keep change, flip, right? So keep the first, change to multiply, and flip the second. I don't need the absolute value anymore, right? We agree? So this is the limit as n goes to infinity of n squared over n plus 1 quantity squared. What happens here? Don't I get infinity over infinity here? Yeah. So I get the limit as n goes to infinity of what? 2n over 2 times n plus 1, right? And then what do I get? Just 2 over 2, so I get 1, right? So we can't use this test now. But what do we already know, right? We already knew it was convergent. We don't need another test, but I'm just just going to apply this ratio test a couple times and see what happens. Let's look at another one. Let's see, I'm doing this example here. So I've got n cubed over 3 to the n. So ratio test. I've got my series negative 1 to the n over n cubed times n cubed over 3 to the n. So you can see every other term here is going to be negative positive, right? But what I'm going to do is, if I take everything to be positive and I can get a sum, right? Then I know for sure if I've got some terms that are negative that are going to get dropped off, then of course I'm still going to get a sum, right? So let's do our ratio test here. So a sub n plus 1 would be what? Negative 1 to the n plus 1 and n plus 1 quantity cubed over 3 to the n plus 1. So I want to write out that next term and then look at the limit of those terms as n goes to infinity of the ratio of those terms. Negative 1 to the n plus 1 all cubed over 3 to the n plus 1 divided by the original series, right? The original nth term. What's the absolute value going to do here? Get rid of the negative ones or positive ones no matter what happens, right? Those are going to go away. That's right. So, but I don't, because I only care about the absolute value of it. So now I'm going to do a keep change flip again. N plus 1 cubed over 3 to the n plus 1 times 3 to the n over n cubed. I already know something about n plus 1 cubed over n cubed. It's going to be, in the long run, the ratio of the leading terms, right? You with me? This is going to be the limit of n plus 1 cubed over n plus 1, n cubed, sorry, times the limit of 3 to the n over 3 to the n plus 1. And of course, that first limit is 1. We already can see it, right, from L'Hopital's. And the other one, we get a 3 to the n over 3 to the n times 3. Nope, I don't need the absolute value anymore, sorry. So I get a limit of 1/3. When you see polynomials, factorials, powers, the ratio test is a good one to look at. Not always conclusive, but if you look at my Paul's notes list here, I think it's my 5th thing I'm checking. Yeah, ratio test, right? And the last thing I'm checking is my integral test. Now I'm going to tell you, use this test on the exam. I'm going to say, use the ratio test, use a comparison test, use an integral test. So I take the guesswork out of it, right? So you're just making sure you're practicing all of these different tests. All right, I needed this one for the next piece I'm going to do, and we're going to start talking about a power series. So I'm going to come back to test. Please be reading with me, but I'm starting 8.5 today, power series. And the power series turned out to be a very useful thing for integrating and differentiating very difficult problems. So what we're looking at is the sum of n equals 0. So the sum of n equals 0 to infinity of c sub n x to the n. So c sub n is my coefficient. X to the n is obviously, right, the variable to a power. And so let's just write out some terms. What do you see here? C sub 0 x to the 0 plus c sub 1 x to the 1 plus c sub 2 x squared, right? You can really get an idea of what's happening. And the most important thing here is we're going to adopt a new thing, is that x sub 0 is going to be equal to 1 when even if x is 0. Of course it's 1. No, of course it's 1 if x is not 0. But we're going to adopt this additional piece that when x is 0, right, I get at least a term. What are you noticing? What's going on here as I move to the next term? I'm multiplying by x. So in some cases, this thing will really be geometric. So in fact, in this case, when n equals 0 to infinity of x to the n, what do I get? I get 1 plus x squared plus x cubed plus dot dot dot, right? So this is really my main power series I want to think about. And what happens, what's pretty funny about this, is I get 1 over 1 minus x. Yeah. So but you're saying 1 plus what? You're putting natural numbers in for?
No, right, when I look at that figure goes like something.
Yeah, well, it does. It does for certain values of x, right? Remember, I'm putting in this placeholder to fill in for everything. So, for example, if I put in x as 1/2, right? So the sum of n equals 0 to infinity of 1/2, right? 1/2 to the n. Yeah. We know this one sums, right? This one sums to 2. Yeah? Because I get what? I get 1/2 to the 0 plus 1/2 plus a 1/4, right? So the rest of this guy, we already, right? We already came up with, it sums to 1. And then plus this other piece, right? We get a sum of 2 there. So yes, we're going to talk about what values of x for this converge for, okay? Now, first of all, we want to kind of demonstrate that it's true. 1 over 1 minus x, though, can get me long division, right? Yes, you with me? So 1 goes into 1 how many times? 1 goes into 1 how many times? One time, right? Come back and multiply, I get a 1 minus x. Change the signs and add. Now 1 goes into x how many times? Yep. Come back and multiply, I get x minus x squared. Change the signs and add. How many times does 1 go into x squared? X squared, right? So we can see, really, you can see the geometric piece in here, right? Remember, I said this thing converges, right? I remember when I got this sum, right? Remember when I got that sum out of the geometric? I had to make sure that that ratio of consecutive terms was less than 1, right? So pretty
Oh, it's what X is like.
exactly when x is less than 1.
Okay,
Yeah.
I'm thinking X2.
Yeah. So when we talk about these power series, we can talk about the convergence. Where's my little chart here? Sorry, don't tell me. Here it is. So for any power series, and this one's got a shift in it, okay, and I typically don't deal with the shifts. So you can see here, this is really just an x to the n if a is 0 here, right? But there's only 3 possibilities that it converges when x is a, when I have the center. It converges for all x's, and it converges for a certain ratio of x's. So the only thing that can happen is that it converges at its center, it converges at 0, it converges for all x's, or it converges for a certain amount of x's, right? And this is called the radius of convergence. So let's go back here. So we already know this radius of convergence, right? But we're gonna do a ratio test to find this radius of convergence. And it seems pretty obvious already what's going to happen here when I do a ratio test with this thing. I'm looking at the limit, right, of as n goes to infinity of the absolute value of x to the n plus 1 over x to the n. Right? Pretty obvious what happens, right? Well, what's going to be left? X to the n's are going to cancel. What's going to be left? I want the limit as n goes to infinity of some absolute value of x, right? And I need that guy to be less than 1. Right? Because I know it's a power series, right? I know it's a power series. I'm just multiplying by the same thing over and over. And I know when that converges. So I need this particular end result, right? So I need absolute value of x is less than 1, or negative 1 is less than x, which is less than 1. So I'm going to look at those ratios, right? Knowing it's geometric, and looking at that ratio limit less than 1, and I'm going to see what happens. Let's do it. Let me look at one more here. So here's a power series, x to the n. Yes, sorry. N factorial times x to the n. So the series n factorial times x to the n from n equals 0 to infinity. Let's start writing out some terms just so we see it again. I get 0 factorial x to the 0 plus 1 factorial x to the 1 plus 2 factorial x squared plus 3 factorial x cubed plus dot dot dot. What do we remember about 0 factorial? That's 1. X to the 0 is 1 in all cases. That's by design. So we can start writing this out again as what? 1 plus x to the 1 plus 2x squared plus 6x cubed. Do you see where I got the 6? 3 factorial is 3 times 2 times 1, right? So we want to find out for what values of x is this thing convergent, okay? For which values of x? So what we do is we look at that ratio test limit. And see what kind of result we get out of it, right? So let's take a look at the limit as n goes to infinity. This is n goes to infinity, right? Of n plus 1 factorial over x to the n, times x to the n plus 1 over the original n factorial x to the n. Obviously, I don't need the absolute value here. But I have to notice a little trick here. Let's see, 5 factorial is 5 times 4 times 3 times 2 times 1, right? Or better yet, 5 times 4 factorial, right? I can see that there's, if I take off that first piece of the product, I still have another factorial left. So this is n plus 1 times n factorial. X to the n times x over n factorial times x to the n, right? So I'm peeling off that first piece from the n plus 1 factorial. So here, those go away, this goes away. What happens to the limit of n plus 1, right, times x as n goes to infinity? Where does this limit go? Where does n plus 1 go? Infinity. So I can get infinity out of this thing, right? Which means it's only going to converge. So when I get the limit out of infinity out of this, I only get convergence at the very, very center, okay? When, right, by the ratio test, this thing diverges for all values of x. So except for 0, except for the center. Right. So remember, we're doing the limit when n goes to infinity, not when x goes to infinity. We're going to let x be whatever it is. Exactly. So we pick an x, right? Yep. So the series, right, converges only when x is 0. And again, the book will talk about x minus a, like a trend, like I've moved a function over. I only care about centered at 0. What do you think is the issue with this one? Why is this one only going to converge when x is 0? And what does it converge to, by the way? When x is 0, it goes to 1, right? It adds up to 1 when x is 0. Yeah, it's silly. What's the issue, do you think? What's happening to this? What's the next term? It's 4 factorial x to the 4th, right? So what do you notice that's the issue? The coefficients are getting giant, right? So even if I put small values of x in, like 1/2, the coefficients eventually overrun, right? Because the coefficients are increasing so fast. Say again?
Factorial.
Yes. All right, I did enough for us to go to a fun part, and that is representing power functions. So what I want to do is take this one little model, right? Sorry. I know that the sum of x to the n from n equals 0 to 1, infinity, sorry, is 1 plus x squared plus dot 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 is 1 over 1 minus x when absolute value of x is less than 1, right? We know this. So we want to look at what happens, and I kind of want you, this is my radius, right? This is the function, and this is the series, of course. And of course, term by term, not a problem, right? But what we want to be able to do is represent another function in the same way. So we're going to look at a couple problems here. Sorry. Oh, there it is. Here we go. So like number 3, I want to represent this as a power series. So what we're doing first is we're taking a power series, getting a function that kind of looks like a power series, and then turn it into a series, okay? So I have 1 over 1 plus x. So my function is 1 over 1 plus x. And I'm saying, wow, that looks an awful lot like the function representation of a power series. So that's what I want to do. I want to see if I can turn it into something like this. And so the way I start is I start by kind of figuring out what I can put in here to get back to my original function. I want to get to here, right? So the question is, what can I put in here? Yep. So I put in the negative x there. And I put that in everywhere else. I put that in everywhere else. So meaning I now have 1 over 1 minus the negative x. And it's got a radius of convergence of that. What happens to the negative there? It cancels, so it's the same radius of convergence. But you can see I'm not trying to do too much here. I'm putting in what I replaced in my function. So n equals 0 to infinity. And what am I going to put in there? Look at everywhere I did it, I had these parentheses, right? And I'm going to do this every time. So what's going in there? Negative x. Then we want to clean that piece up. right? So now we have 1 over 1 plus x is equal to the sum of n equals 0 to infinity of negative 1 to the n, x to the n. That's what I want. I want to take the coefficients, the signs, the coefficients, and the x terms and kind of clean them up as much as I can. So what happens? What are my terms now? Yep. Minus x, then x squared, yep. Yep. Nice. Now, I've got my series representation. The way I check my radius of convergence is do the ratio test. But I'll get exactly the same thing. I'll get the limit of x, and I want it to be less than 1. So it's kind of nice that you can get the radius of convergence just by putting into there. Let's do another one. Number 5 is good. 2 over 3 minus x. So there's my function. I want to come up with a power series representation. Does it kind of look like the 1 over 1 minus x? Hell yeah, right? Definitely does, right? And remember, I'm going to figure out what I had to put here. I'm going to figure out what I have to put here. Yes? And then what I have to put here. But there's another problem, isn't there? What is the problem? The 3. You remember? Remember what we did with the 3? We're going to divide everything by 3 and then see what we got. So I got now a 2/3 out here, right? And inside I have a 1, sorry, 1 over 1 minus x cubed. X over 3, sorry. Yeah. So 1 over 1 minus x over 3. And now you can see what I'm putting into my power series rep, right? Exactly. So I have 2/3 out here now. I have 2/3 out here now, right? And I'm going to have 2/3 out here now. And what am I putting inside? X cubed, right? I don't need this 2/3, sorry. Just what's inside. X over 3. I keep doing that. My brain is not working. But look at my radius of convergence now. Right? My radius of convergence is within 3, right? X over 3 in the absolute value. Yep. So we just want to clean up this series a little bit if we can, right? So what do I have? 2/3 times the sum of x to the n, 1/3 to the n, right? X to the n. Trying to get my coefficients, my signs, my coefficients, and my x terms separate. Can I do anything with this? What do you think? 2 times what? 3 to the what? So I want to try and clean up things as much as I can, make a nice looking series. I can leave the 2 outside, I can leave the 3 outside, but this is more likely what the book's going to show you. Let's do another. What do you think of 1 to 10 there? Which one looks kind of interesting to you? 8? 8? Yep. So x over 2x squared plus 1. So I've got a function, x over 2x squared plus 1, that I want to do a power series representation for. Well, I want it to look like some version of this, right? And I'm going to plug in there. I'm going to plug in here. And I'm going to plug in here once I get there. All right, well, I definitely don't like the x upstairs, so I'm going to factor that out. And it looks like I'm pretty much done. I want a negative in front of that 2x squared, right? Of course, I have to cancel it, right? But you can clearly see what I'm putting in for my radius, for my series, and, right, I already have that first one.
Oh, okay.
Yeah,
Remember that x is a constant.
that's right.
If you could just pull that x out.
Exactly, exactly. So what I'm going to do is I'm going to really just focus in on this piece right now, right? And then no, I'm going to have to multiply by x after, right? You with me? So what do I get here? I get a minus 2x squared, a minus 2x squared, a minus 2x squared. And let's focus in on the series. What do I get? I get a negative to the end. Remember, I want to treat this as a sign, a coefficient, just a 2, right? And an x term. Say again? It's just the norm. I want to think of the sign, positive, negative terms, what the coefficient is, and what the variable is. Yep. Now, this is almost my f of x, right? But I need to do what to it? Multiply by x, correct? And when I do that, what do I get as my final series? The series of negative 1 to the n, 2 to the n, x to the 2n plus 1. Yeah, is that simple? And what's my radius of convergence? Well, the negative 2 is going to just become a positive 2. So I'm going to need, what, x squared in absolute value less than 1/2, right? But I want to know what x's I can use, right? So what do I go further with this, right? I'm going to take a square root. So I need the absolute value of x to be less than rad 2 over 2, or square root of 1/2, right? Yeah. Well, it's kind of nice to I think these are fun, but I would like. How could I possibly come up with a series for something like number 11 here? So here's number 11. I want to find a series for f of x equal to 1 over 1 plus x quantity squared. Remember, if I have a series for this, I have just a bunch of polynomial terms, right? I've got an x to the 1, an x squared, et cetera, and those are all easy to deal with: integration, differentiation, etc. So we're trying to just figure out ways how we can turn complicated functions into sums of polynomials. That's what we're working on. So this one looks an awful lot like what I want, right? It looks an awful lot of what I want, except for the square. And so you're supposed to kind of recognize here that if y equals 1 over x, y prime is minus 1 over x squared. So it looks like perhaps we have a derivative, right? A derivative of the function that we can turn into our series, right? So it looks like I might want to integrate this thing. So the integral of f of x is the integral of 1 over 1 plus x quantity squared, right? And what is that? No, 1 plus x squared would be, right? So this is 1 plus x quantity squared. Well, we're just going to do a u sub here, aren't we?
Yeah.
Yeah. So if u is 1 over x, right? Du is just dx, yes? So it looks like I have the integral of 1 over u squared du. So what is that? The integral of u to the minus 2 du, how's that? So I'm going to add 1 and divide by the nu, right? So it looks like I get the opposite of u to the minus 1, the opposite of 1 over u. So the opposite of 1 over, what was u? 1 plus x. Oh, look at that. That now I can get my power series representation of, and then do what with it? Remember, I wanted a power series for f of x, not the integral of f of x. So what am I going to have to do after I get my power series? Nobody? what am I going to have to do at the end to get my representation of the function? Differentiate, right? So I get the opposite of the series from n equals 0 to infinity of negative 1 to the n x to the n. Yes, this is the integral, right? This is the integral of f of x. So what do I want to do? And I could play around with the right-hand side before I differentiate or after. It's not really going to change anything, okay? So meaning I could pull this negative in, right? And turn this thing into a negative 1 to the, right? Yes, you with me? The sum of n equals 0 to infinity of negative 1 to the n plus 1, x to the n. Yes, you with me? So how am I going to get f of x as a series? Is I'm going to differentiate. So, what do you think? Well, I could write these out term by term, right? And differentiate term by term. Yes? So it sounds like maybe what we should do first. So what's my first term? Nice. So I'm going to go negative, positive, right? And then x to the 0 taken care of already. So the next one is x to the 1, right? And then a negative x squared. And then a positive x cubed, right? You with me? So let's differentiate. That's pretty friggin' easy. What happens to the derivative of negative 1? Yep. So I've got 0 plus 1 minus 2x plus 3x squared minus 4x, sorry, 3x squared, right? Minus 4x cubed plus etc. So I certainly don't need the 0. And now I write my series. Well, it doesn't seem so good to start at 0, especially because I can see the first term's got a 1, the second term's got a 2, the third term's got a 3, right? So maybe I should start this at n equals 1. What about my sign? Nice, n plus 1. And then I need an n, right? There's my coefficient. And then I need an x to the what? N minus 1. If you take a look at my original function of what I had originally, d dx, what did I have? I gotta scroll up for a second. Of the sum of n equals 0 to infinity of negative 1 to the n plus 1. Is that what I had? Yep. times x to the n. Do you see what happens if I just take the derivative of the series? Do I care about the derivative of the coefficients? No. All I care about is the variables, right?
Yeah.
And what happens when I take the derivative of x to the n? N times x to the n minus 1. Yep, so look, I have n equals 0 to infinity of negative 1 to the n plus 1 times n times x to the n minus 1. That's exactly what I had. But notice I'm starting at a different index, right? If I start at that index, I get a nonsense term out of it. You see, let's start writing out my terms here. When n is 0, I get a negative, and then for x, I get a 1 over x. And then I get the rest of the terms, right? Yeah. So, but of course that first term is nonsense. Oh, 0. Yeah, so I put in 0 for n. Thank you. Thank you. Yeah, that's even better. But it either will be 0 or it'll be a nonsense term. I need this to be only powers of x. Positive powers of x, right? Polynomials, not 1 over x. But if I do write out that first term, though, you're right. Negative 1 to the 0 plus 1 times 0 times 1 over x. I'm pretty sure I remember all of my nonsense terms will get knocked out anyway. Okay? So plus the good stuff, right? But you can see my process. My process is, hey, let me write out terms. Let me differentiate that way. Let me differentiate with the whole series. And then maybe I'll have nonsense terms, so let me rewrite it. So whether I rewrite it at the beginning or rewrite it at the end, right? Like I said here, rewrite it at the beginning, right? Figure out what my terms are, or do it at the end. Once I figure this thing out, then write my series. If I do it term by term, right, the nonsense terms are going to go away anyway, and then write out the series. What's kind of nice is to think about, and I want you to think about this when you're doing problems like this, is could I write this as x to the n? Could I start it? Could I make it look a little bit better? Or what would happen if I changed n minus 1 to n, right? That's what I'm kind of asking you. How can I think about this? Like if I started this at 0, right? You with me? If I started this at 0, I'd have a 1 over x term here, right? Yeah. So what happens if I want to start it at n equals 0? How can I change that term, right? How can I change that one term? I want an x to the n. That's what I'm saying, right? Yeah. So what happens to everything else? Right? I want to know what to put on my negative 1 and what to put as my n. Well, if n minus 1 changed to n, what did I add to the n minus 1? I added 1, right? Yeah. So I'm going to add 1 everywhere else. So I get an n plus 1, and I get an n plus 2. Now, n plus 2 starts even, right? So I don't really need the n plus 2. I just have to have it started even. Exactly. So I can make that prettier too. So negative 1 to the n times an n plus 1 times an x to the n, all starting at n equals 0. And you'll see, and all I'm asking you to do is when you do a problem, see if you can rewrite it. the book likes to keep the variables to the n. So when you end up with a variable to the n minus 1 or variable to the n plus 1, you want to see if you rewrite it, does it get prettier? That's all we're trying to do here. Look at this thing. Look at what happened, right? What did I have? All of a sudden now I had what? I had 1 over 1 plus x quantity squared, right? And now I've got all of a sudden this series from n equals 0 to infinity, negative 1 to the n times an m plus 1 times an x to the n. And that's the game. Can I come up with a power series representation for functions? Here comes the best one ever.
Yep.
Best one ever. And I always put it on every test. I want f of x is equal to the ln of 1 minus x. Say again? Yeah, back one. Sorry. We want pictures, or where are you? Oh, yeah. No, that's the Maclaurin. We'll do that with Maclaurin. So you're going to see we have this rational function now, right? But now I have a rational function that I can write as a sum of polynomials. And this is what we're trying to do. Then we're going to get an exponential function as a sum of polynomials. Then we're going to get trig functions as a sum of polynomials. So we're just kind of walking down the path of where we can turn things into polynomials, right? Depending on what it kind of looks like. Yeah. Okay, here it is. It doesn't look like the sum of polynomials to me, right? I want a power series for this. This is the stuff that I think is fun, but, I'm a nerd. So find a power series for this. Well, it doesn't look anything like what I want, right? What do I want? I want some representation of 1 over 1 minus x, right? Well, it looks an awful lot like it, doesn't it? What is that? Not the integral, the derivative. Yep, so d dx of f of x, it's got to be d dx of the ln of 1 minus x. And if you remember that from our last test, or from Calc 1, I need the derivative of the inside over the inside, right? So negative 1 over the inside. Well, that's almost exactly what we need, right? So the derivative of my original function is the opposite of that original power series, isn't it? So the opposite of the sum of x to the n.